In abstract algebra, the symmetry group of an object is the group of all transformations under which the object is invariant with composition as the group operation. For a space with a metric, it is a subgroup of the isometry group of the space concerned. If not stated otherwise, this article considers symmetry groups in Euclidean geometry, but the concept may also be studied in more general contexts as expanded below. Introduction. The objects may be geometric figures, images, and patterns, such as a wallpaper pattern. For symmetry of physical objects, one may also want to take their physical composition into account. The group of isometries of space induces a group action on objects in it. The symmetry group is sometimes also called full symmetry group in order to emphasize that it includes the orientation reversing isometries under which the figure is invariant. The subgroup of orientation preserving isometries that leave the figure invariant is called its proper symmetry group. The proper symmetry group of an object is equal to its full symmetry group if and only if the object is chiral. Any symmetry group whose elements have a common fixed point, which is true for all finite symmetry groups and also for the symmetry groups of bounded figures, can be represented as a subgroup of the orthogonal group O by choosing the origin to be a fixed point. The proper symmetry group is then a subgroup of the special orthogonal group SO, and is therefore also called rotation group of the figure. A discrete symmetry group is a symmetry group such that for every point of the space the set of images of the point under the isometries in the symmetry group is a discrete set. Discrete symmetry groups come in three types. Finite point groups, which include only rotations, reflections, inversion and roto-inversion. They are just the finite subgroups of O. Infinite lattice groups, which include only translations, and infinite space groups, which combines elements of both previous types, and may also include extra transformations like screw axis and glide reflection. There are also continuous symmetry groups, which contain rotations of arbitrarily small angles or translations of arbitrarily small distances. The group of all symmetries of a sphere O is an example of this, and in general such continuous symmetry groups are studied as Lie groups. With a categorization of subgroups of the Euclidean group corresponds a categorization of symmetry groups. Two geometric figures are considered to be of the same symmetry type if their symmetry groups are conjugate subgroups of the Euclidean group P, where two subgroups H1, H2 of a group G are conjugate, if there exists GG such that H1 equals G-1 H2 grams. For example, two 3D figures have mirror symmetry, but with respect to different mirror planes. Two 3D figures have threefold rotational symmetry, but with respect to different axes. Two 2D patterns have translational symmetry, each in one direction. The two translation vectors have the same length but of different direction. When considering isometry groups, one may restrict oneself to those where for all points the set of images under the isometries is topologically closed. This includes all discrete isometry groups and also those involved in continuous symmetries, but excludes for example in 1D the group of translations by a rational number. A figure with this symmetry group is non-drawable and up to arbitrarily fine detail homogeneous, without being really homogeneous. One dimension. The isometry groups in one dimension where for all points the set of images under the isometries is topologically closed are the trivial group C1. The groups of two elements generated by a reflection in a point, they are isomorphic with C2. The infinite discrete groups generated by a translation, they are isomorphic with Z, the additive group of the integers. The infinite discrete groups generated by a translation and a reflection in a point, they are isomorphic with the generalized dihedral group of Z, DIH, also denoted by D infinity. The group generated by all translations, this group cannot be the symmetry group of a pattern. It would be homogeneous, hence could also be reflected. However, a uniform one-dimensional vector field has this symmetry group. the group generated by all translations and reflections in points. They are isomorphic with the generalized dihedral group of R, DIH. See also symmetry groups in 1 dimension, 2 dimensions. Up to conjugacy, the discrete point groups in 2-dimensional space are the following classes. Cyclic groups C1, C2, C3, C4, where Cn consists of all rotations about a fixed point by multiples of the angle 360 degrees, n. Dihedral groups D1, D2, D3, D4, where the n consists of the rotations in Cn together with reflections in n axes that pass through the fixed point. C1 is the trivial group containing only the identity operation, which occurs when the figure has no symmetry at all, for example the letter F. C2 is the symmetry group of the letter Z, C3 that of a triskelion, C4 of a swastika, and C5, C6, etc. are the symmetry groups of similar swastika-like figures with 5, 6, etc. arms instead of 4. D1 is the 2-element group containing the identity operation and a single reflection, which occurs when the figure has only a single axis of bilateral symmetry, for example the letter A. D2, which is isomorphic to the Klein-4 group, is the symmetry group of a non-equilateral rectangle. This figure has 4 symmetry operations. The identity operation, 1 two-fold axis of rotation, and 2 non-equivalent mirror planes. D3, D4, etc. are the symmetry groups of the regular polygons. The actual symmetry groups in each of these cases have 2 degrees of freedom for the center of rotation, and in the case of the dihedral groups, 1 more for the positions of the mirrors. The remaining isometry groups in 2 dimensions with a fixed point, where for all points the set of images under the isometries is topologically closed, are the special orthogonal groups consisting of all rotations about a fixed point. It is also called the circle group S1, the multiplicative group of complex numbers of absolute value 1. It is the proper symmetry group of a circle and the continuous equivalent of Cn. There is no geometric figure that has as full symmetry group the circle group, but for a vector field it may apply. The orthogonal group O consisting of all rotations about a fixed point and reflections in any axis through that fixed point. This is the symmetry group of a circle. It is also called DIH as it is the generalized dihedral group of S1. For non-bounded figures, the additional isometry groups can include translations. The closed ones are the 7 frieze groups, the 17 wallpaper groups. For each of the symmetry groups in 1 dimension, the combination of all symmetries in that group in 1 direction, and the group of all translations in the perpendicular direction. Ditto with also reflections in a line in the first direction. 3 dimensions. Up to conjugacy, the set of 3-dimensional point groups consists of 7 infinite series and 7 separate ones. In crystallography they are restricted to be compatible with the discrete translation symmetries of a crystal lattice. This crystallographic restriction of the infinite families of general point groups results in 32 crystallographic point groups. The continuous symmetry groups with a fixed point include those of cylindrical symmetry without a symmetry plane perpendicular to the axis. This applies, for example, often for a bottle. Cylindrical symmetry with a symmetry plane perpendicular to the axis. Spherical symmetry. For objects and scalar fields, the cylindrical symmetry implies vertical planes of reflection. However, for vector fields it does not. In cylindrical coordinates with respect to some axis, has cylindrical symmetry with respect to the axis if and only if and have this symmetry, i.e., they do not depend on phi. Additionally, there is reflectional symmetry if and only if. For spherical symmetry there is no such distinction, it implies planes of reflection. The continuous symmetry groups without a fixed point include those with a screw axis, such as an infinite helix. See also subgroups of the Euclidean group. Symmetry groups in general. In wider contexts, a symmetry group may be any kind of transformation group, or automorphism group. Once we know what kind of mathematical structure we are concerned with, we should be able to pinpoint what mappings preserve the structure. Conversely, specifying the symmetry can define the structure, or at least clarify what we mean by an invariant geometric language in which to discuss it. This is one way of looking at the Erlangen program. For example, automorphism groups of certain models of finite geometries are not symmetry groups in the usual sense, although they preserve symmetry. They do this by preserving families of point sets rather than point sets themselves. Like above, the group of automorphisms of space induces a group action on objects in it. For a given geometric figure in a given geometric space, consider the following equivalence relation. Two automorphisms of space are equivalent if and only if the two images of the figure are the same. Then the equivalence class of the identity is the symmetry group of the figure, and every equivalence class corresponds to one isomorphic version of the figure. There is a bijection between every pair of equivalence classes. The inverse of a representative of the first equivalence class, composed with a representative of the second. In the case of a finite automorphism group of the whole space, its order is the order of the symmetry group of the figure multiplied by the number of isomorphic versions of the figure. Examples: isometries of the Euclidean plane. The figure is a rectangle. There are infinitely many equivalence classes. Each contains 4 isometries. The space is a cube with Euclidean metric. The figures include cubes of the same size as the space, with colors or patterns on the faces. The automorphisms of the space are the 48 isometries. The figure is a cube of which one face has a different color. The figure has a symmetry group of 8 isometries. There are 6 equivalence classes of 8 isometries, for 6 isomorphic versions of the figure. Compare Lagrange's theorem and its proof.